Hello, and welcome to the video lecture for topic 24, radical reactions. So far in Chem 201, all of the reaction processes that we have seen involve the movement of two electrons together. In these processes, all of the bond breaking events are known as heterolysis. A very simple example of heterolysis, if I have some atom A connected to some atom B, our arrow pushing that we've used so far moves both electrons from the bond to atom B, leaving A with a positive charge, and in our hypothetical example, atom B with a negative charge. This is known as heterolytic bond cleavage. And the end result is that the electrons after the bond breaking event are not evenly distributed. One of the atoms, the more electronegative atom, has taken both of those electrons. And so we consider these to be polar or ionic processes. What we're going to see here in topic 24 is that there is another way that a bond can break. And in this new way is called bond homolysis, where we have two atoms. Again, here we're going to say A and B. But this time when the bond breaks, the electrons will be evenly distributed between the two atoms. One electron will go to atom A, and one electron will go to atom B. This is a radical process. We have created a species that has an unpaired electron. These are known as radicals, and the arrow pushing for them is similar but slightly different than the arrow pushing for our polar and ionic processes. Right? First of all, when we do our polar and ionic processes, we're moving two electrons at once, and the head of our arrow has two barbs to it to denote that two electrons are being moved by that arrow. When we do bond homolysis, our radical processes, we're only moving one electron per arrow. And so this arrow is a fishhook arrow. It starts with the electrons, but it ends with a single barb. That means to show the movement of both electrons in this bond, I have to use two arrows, and two of these fishhook arrows to show that the bond breaks, one electron goes to atom B, and one electron goes to atom A. Now, these are our bond breaking processes. How about our bond making processes? Well, when we were doing our polar and ionic types of reaction mechanisms, we saw that if I had some species A and some species with a lone pair B, I used an arrow from the lone pair on B going all the way to atom A with two barbs on the head of the arrow to show that I had formed a new bond. So again, these are our polar or ionic processes. However, in our radical processes, we have to bring two electrons on two different atoms together. So again, we're going to use a pair of fishhook arrows, one fishhook arrow for each electron we need to move. But instead of having that arrow end at the atom we're going to, it's going to end in the region of space where the bond forms. So we're forming a bond between A and B. So I'm going to start my arrow here at B, end it in the region of space between them. Similarly with A, it ends in the region of space between them. And that denotes to us that we are taking the electron from radical A, electron from radical B, combining those together to form a new bond connecting atom A, to atom B. So again, this is for our radical processes. The last thing we need to be able to show is resonance in our radical processes. And so let's take a look at a hypothetical radical. Here I have atom A connected to atom B, which is connected to atom C, that has an unpaired electron. And now I'd like to draw a resonance structure for this, where I delocalize that radical, the same way I would delocalize a positive or negative charge in a polar or ionic process. The same rules from polar and ionic processes with this new added style of arrow, fishhook arrow rules, are going to be combined. So what I see is that if I move that unpaired electron off of atom C, I'm going to use it to create a new bond between atom C and atom B. I'm going to take one of the electrons in a bond between atom A and atom B and bring it again, both of these fishhook arrows end in the region of space between the two atoms where I'm going to form my new bond. Finally, I've dealt with one of the electrons in this pi bond between A and B, but I also need to deal with the other electron in the pi bond between A and B and move that over to atom A. Here now I use my same resonance arrow that we've seen in our polar and ionic processes, and now I can draw a new resonance structure for this hypothetical radical where I have delocalized that unpaired electron to a new atom. So now that we've seen kind of how this arrow pushing works, the last thing that I'd like to do before we get into a little bit of reaction chemistry is to talk to you about the stability and formal charges of radical species. So the stability of carbon-centered radicals parallels the stability of carbocations, and for the same reasons, hyperconjugation and resonance. So the stability of carbon-centered radicals, we have our benzylic radicals are the most stable, followed by allylic, followed by tertiary, then secondary, then primary, and then methyl. Now, unlike carbocations, primary and methyl radicals do form. Right? We are able to form non-resonance stabilized primary radicals, and we are able to form methyl radicals as well. So that's the only difference between the stability of radicals and the stability of carbocations. While we cannot form a primary or methyl carbocation, we can easily form a primary or methyl carbon radical. Right? So again, this benzylic is going to be most stable, and our methyl is going to be least stable. Okay, so now let's just talk about formal charges on radicals. So we'll take two examples, right? I'm going to take bromine, have that undergo homolytic bond cleavage to give two bromine radicals. And we're also going to look at taking methane homolytically breaking one of the two carbon-hydrogen bonds to form a carbon-centered radical and a hydrogen radical. Now, let's go through the exercise of calculating the formal charge using the equation that we learned earlier this term, where formal charge equals the number of valence electrons minus the number of bonding pairs minus the number of non-bonding electrons. So for our bromine example, bromine, right, being a halogen, in its neutral state has 7 valence electrons. In this bromine radical that we've formed, there are 0 bonding pairs, but we see that we have 1, 2, 3, 4, 5, 6, 7 non-bonding electrons overall to give it a formal charge of 0. Now let's look at carbon. Carbon typically has 4 valence electrons. When we form this carbon-centered radical, we have 1, 2, 3 bonding pairs and 1 non-bonding electron, also giving it a formal charge of 0. And then finally, so this was for carbon, this was for bromine, and then finally for hydrogen, we have hydrogen normally has 1 valence electron. Our hydrogen radical here has no bonding pairs, and it has 1 non-bonding electron. Once again, a formal charge of 0. So the atom that bears the radical itself will typically have a formal charge of 0. That is not to mean that somewhere else in the molecule, some other atom, doesn't have a formal charge to it. We're just talking about the formal charge of the atom that has the unpaired electron. And that typically will be for us 0 is a formal charge of any atom that bears an unpaired electron, any atom that is the center of that radical. Okay, so what's left for us to cover here in topic 24 is the reactions that we are going to see and the reactions you need to know that involve radical species. I am going to go through these reactions one at a time and show you specifically all of the arrow pushing that you're going to need to know for this topic. Okay, so I'm going to clear off the board and we'll come right back with radical halogenation. All right, so the first reaction or radical chain mechanism that we need to see is radical halogenation. Now, the mechanism I'm going to put up is I'm going to use bromine as my halogen for this mechanism. However, everything you see here also applies to if I were to use chlorine. However, as you'll see in the POGIL activity and you're reading in Sorrel, selectivities vary a small amount. I'm going to narrow down the alkane that I use for this specifically to ethane, which keeps things nice and simple. So radical halogenations go through, and all radical chain mechanisms go through a series of defined steps. The first of these steps is known as initiation, wherein the case of bromine and chlorine, a photon of light actually causes cleavage of that bond to generate 2 bromine-centered radicals. And so this is our initiation, hang on. While your chemistry has gotten better this semester, my spelling has not. That's our what's known as our initiation step. That generates for us 2 bromine radicals. From here, we have what's known as our first propagation step. So as I said, I'm going to use ethane for my alkane that I'm going to halogenate. And what we find is that this bromine radical removes a proton from ethane to create a carbon-centered radical. Again, remember, I'm taking an electron from the carbon-hydrogen bond, an electron from bromine, bringing them together. My arrows meet in the space where that new bond will form. These don't go to an atom. However, because I'm taking one of the electrons from this bond, leaving it on carbon, that arrow does go to the atom. We want to make sure that we're drawing our arrows correctly. So what this forms for us is a molecule of HBr and a new carbon-centered radical. That carbon-centered radical goes on in a subsequent step to react with a new molecule of bromine where we're going to end up attaching a bromine to our carbon radical, simultaneously generating a new bromine radical That's going to give us our halogenated alkane. And a new bromine radical that can go back here and repeat this process. These two steps are known as propagation steps. This is known as propagation 1, and this is known as propagation 2. When we look at our propagation steps, a radical that is both consumed and created during propagation is known as the chain-carrying species. So in propagation, bromine radical is the chain-carrying species. Right? It is the radical that keeps this process going, keeps the process going, because it is both consumed and produced. Okay. What's left is, how does this reaction end? I can't just keep creating radicals all the time. Eventually, these highly reactive species, these unpaired electrons, they want to form bonds and end this story. And so there are three processes by which this reaction terminates. Two of them are known as recombination. So the first is, I can have a bromine radical find another bromine radical. Those can combine to regenerate Br2. Or I can have an ethane radical find another ethane radical. And those can combine to form a molecule of butane. Right? Both of these are termination steps that are called recombination. The third option also occurs between two of my ethane radicals, but a slightly different process occurs. So I'm going to draw this out just a little bit more explicitly. So here's my carbon-centered radical on one of my ethane molecules. And here's my carbon-centered radical on my other ethane molecule. And what happens is that one of these ethane radicals removes a hydrogen from the other. This other electron in the carbon-hydrogen bond goes between the two carbon atoms, and the end result of all of this is that this molecule here now has a carbon-carbon double bond, and this ethane molecule becomes fully saturated again. Whoop. Few too many carbons there, excuse me. Becomes fully saturated again. So all three of these are known as termination steps. However, these two are known as recombination because we are combining two radicals together, whereas this step down here is known as disproportionation. All right, so this is the kit and caboodle for radical halogenation. And again, all of the steps that you see here are applicable to either using bromine or chlorine to do a halogenation. The next thing we're going to look at is allylic and benzylic bromination using N-bromosuccinimide. I'm going to go ahead and clear off the board, and we'll come back and take a look at that mechanism next. For benzylic and allylic brominations using N-bromosuccinimide, we are not able to directly generate a bromine radical the way that we were with Br2. N-bromosuccinimide reagent does not directly generate a bromine radical. We need to initiate our radical process with a different type of initiator. So what I'm drawing up here is a molecule known as benzoyl peroxide, which is a pretty handy radical initiator for situations where we need to start generating them, and we can't just do it using light directly on some species that can give us exactly what we want. What we can do with benzoyl peroxide, though, is, typically speaking, when subjected to heat, the first thing that happens is this oxygen-oxygen bond breaks to create two oxygen-centered radicals. So we have two of these now that look like carboxylic acids but a radical with no proton. And these can further decompose to generate two phenyl radicals and two molecules of CO2. Now, that phenyl radical is going to be pretty useful for us, but before we go any further, I'd like to take a look at a background polar process that's going to be happening continuously through this reaction. This is going to be where we get our Br2 source. Quick note about Br2, the actual liquid bromine is incredibly toxic, and the fumes of it are known to cause blindness. So we'd like to avoid using Br2 wherever possible. And so for doing our benzylic and allylic brominations, we've developed a reagent known as N-bromosuccinimide, which we can use with a small amount of HBr to consistently generate Br2 for us. So this starts off, and again, this is now a polar process. This is not a radical process. We protonate that carbonyl, once that carbonyl is protonated, the bromine anion we just generated can form a bond to the bromine bonded to that nitrogen. That pushes up now into that oxygen, and this produces Br2, which we can use for our radical process in a moment. What you should notice is that the end result is this succinimide now has something that looks a lot like an enol. This is going to undergo tautomerization, and we have acid around, so you should be able to correctly do arrow pushing for the tautomerization of this to succinimide. It's a lone pair there, to succinimide. So now that we've got our Br2 molecule that we can use, we've got a phenyl radical, the first thing that's going to happen So that phenyl, one of those phenyl radicals is going to interact with bromine to give bromobenzene and another bromine radical. So we can consider this our initiation step. From there, our bromine radical can find an allylic or benzylic hydrogen. Here I'm going to show a benzylic example. And it is able to remove that allylic or benzylic hydrogen and create a benzylic benzylic radical. So there's our benzylic radical, and we've generated a molecule of HBr as well. This is propagation 1. Now, from there, my benzylic radical can come and find a new molecule of bromine It takes one of these bromine atoms, generating a new bromine radical, and my benzylic bromide. And this is propagation 2. From there, this reaction can shut down via the termination processes that we saw for radical halogenation, right? We can have radical recombination between two bromine radicals. We can have radical recombination between two benzylic radicals, or we can have radical disproportionation between two benzylic radicals as well. So I'm not going to review those termination mechanisms. Based on what you saw in the first radical halogenation mechanism, you should be able to work out those products. And I feel it's a good exercise for you to sit down, push those arrows, and see what happens. So here we go. And this, everything you see here would work just as well with an allylic system as it does with the benzylic system. So the next two things, or the next one that I'd like to look at with you is a couple that involve metals. And so one of these is going to be for cleaving benzyl ethers, and the other is going to be for reducing alkynes. Okay, so the next mechanism we're going to look at is cleaving benzyl ethers with palladium and hydrogen gas. Now, this is not a radical chain mechanism, right? We're not going to see propagation, initiation, termination, but we do want to have a sense of what's happening in this reaction. So in the first step of this reaction, palladium metal interacts with hydrogen gas to form two hydrogen-centered radicals. From here, we can take a benzyl ether so we have a benzyl group, some other group that are connected by an oxygen. This is a benzyl ether. And one of our hydrogen radicals, and these actually come together to cleave this carbon-oxygen bond. One of the electrons will come to form an oxygen-hydrogen covalent bond, and the other will go to sit on that benzylic carbon. And so the product of our first step is this benzylic radical. It's a resonance stabilized radical. It's very low energy in terms of our different radicals, carbon-centered radicals that we can form. And we have also formed one molecule of alcohol from the other side of our benzyl ether. In the second step, that benzyl radical we just formed reacts with our other hydrogen radical in what can be considered a radical recombination step, if you'd like, but that's not really an appropriate descriptor for it, to give us some sort of a toluene derivative. Remember, toluene is the name for methylbenzene. Of course, I have not shown any substituents on here, but there very well could have been. So this is the arrow pushing mechanism for cleavage of benzyl ethers using palladium and hydrogen gas. Going to make a little space. We'll come back and see what is known as the dissolving metal reduction. Okay, so our dissolving metal reduction sometimes known as the solvated electron reduction. So when we do this reaction, the first thing we do is we take liquid ammonia and we combine that with sodium metal, right? So this is sodium metal with we put that little 0 there to indicate that it is the metal and not a cation of the metal. What this does is it liberates an electron from the sodium atom to generate a sodium cation, and a free electron surrounded by or solvated by our ammonia molecules. And so this is why we call it a solvated electron, right? Literally, we have created a free electron that is surrounded by ammonia. We also sometimes call this a dissolving metal reduction because once we add the metal in, it literally begins to dissolve. And our indicator that we have formed our solvated electron is that this solution becomes a lovely blue color, somewhere from a light blue to a dark blue, depending on the concentration of metal or the amount of metal that you add in. So once we have this, we can now use this solvated electron in combination with ethanol to reduce an alkene to a to reduce an alkyne to a transalkene. So let's go ahead and begin with an internal alkyne. And we see that the first thing that occurs is this solvated electron is going to combine with one of the electrons in a pi bond of our alkyne. The other electron from that pi bond will move to a carbon atom. And what we will form is what is known as a radical anion. And it's an anion because we brought these two electrons together and they're going to end up on this carbon atom. So we have 2 electrons, 3 bonds to this carbon atom, which means it has a negative charge. We have both the radical and on a different atom a negative charge. This is known as a radical anion. This radical anion will interact with a molecule of ethanol in a polar arrow pushing step to protonate at that anion. Remember, we've got that sodium floating around the entire time, so to balance our negative charge, there's our Na+. And here now, we have gotten rid of our anion, we have protonated one of the carbons, protonated one of the carbons of the alkyne. And now we have the ability for this to, because this is, we can consider an sp2 hybridized carbon on our radical here. We have a p orbital that has one electron in it in an sp2 hybridization. In an sp hybridization, right? This electron can go to either top or bottom. The second electron, when it comes on from our dissolving metal in our next step, right? We can do this. This adds, because of the planarity of this this linear planar sp hybridized carbon radical, right? That electron can add and move this R group from either face, and move this R group in such a fashion that the least steric hindrance in our alkyne is formed. And so we end up with a new anion where we now have a negative charge, where we now have a negative charge on this sp2 hybridized carbon, right, where we've put our two R groups on opposite faces of our forming alkene in order to reduce steric hindrance, and another molecule of ethanol can come along. We still have sodium cations in our solution. Another molecule of ethanol can come along to provide us with a proton to form our now transalkene. And along the way, we formed two molecules of sodium ethoxide. So this is the arrow pushing that I expect you to know for our dissolving metal reduction. It's a combination of radical processes and polar processes which allow us to convert an alkyne to a transalkene. Okay. We have one more reaction for this topic, so I'm going to clear off the board and come and look at the last one. Okay, our last reaction for topic 24 is going to be the peroxide-mediated addition of HBr across an alkene. So we're going to use a peroxide to add HBr across an alkene, an alkene. But what we're going to see is that use of this peroxide to add HBr will give us anti-Markovnikov orientation of that HBr. So the peroxide that we're going to use is an organic peroxide, and perhaps the most common organic peroxide for this purpose is T-butyl peroxide. And so in the presence of heat, T-butyl peroxide breaks up into two oxygen-centered radicals. Now, this oxygen-centered radical locates a molecule of HBr, and the oxygen radical takes the hydrogen atom from HBr to produce a bromine radical and tert-butyl alcohol. This is our initiation step. From there, our bromine radical can locate an alkene and it adds such that the most stable radical is formed. We are following sort of Markovnikov's rules, but because bromine is the first to add in this mechanism, under this process, the most stable radical will result in what looks like an anti-Markovnikov addition. So here now, we could have formed a primary radical or a secondary radical. The secondary radical is going to be more stable. So here we formed our secondary radical in propagation step 1. This new carbon radical can find a new molecule of HBr and remove the hydrogen from it to give our brominated alkene and another bromine radical in our propagation 2 step. And as we've seen with radical chain mechanisms earlier, for our radical halogenation that we saw earlier, right, or our N-bromosuccinimide bromination of benzylics and allylics, once we get to propagation 2, now we can begin to look for termination mechanisms, either radical recombination of 2 bromine radicals, radical recombination of two of these carbon-centered radicals, or radical disproportionation between 2 of these carbon-centered radicals. Now, just to show you what I mean by anti-Markovnikov orientation, if you recall from back from when we first started electrophilic addition a number of topics ago, when we added HBr across a carbon-carbon double bond, in the absence of any radical species, what happened was that we added our hydrogen atom such that the more stable carbocation was formed. In this instance, that would be the secondary carbocation. Reaction with the bromine nucleophile gave us our final product, right? And so we can see now the difference in this Markovnikov product versus from our radical process using peroxides, which produces what could be considered an anti-Markovnikov product. So that's what I've got for you for radical reactions. There is quite a bit of arrow pushing that we went through here. We've had a couple of lighter topics, specifically 1,4 addition of dienes, but we needed to really get through this, and all of the mechanisms I've shown you here are mechanisms you're going to be expected to know for both Chem 201 and 202. Don't try to think about memorizing these. Instead, try to understand what's fundamentally happening step by step. That usually ends up being the more successful way of learning these different reactions. All right, as always, if you have any questions, please bring them to me in conference, office hours, lecture, or make an appointment to see me. And thank you for your time.